All right, in this video, we're going to be talking about log laws. Log laws or logarithm laws are similar to exponent laws in that they're ways that will help you sort of manipulate logarithmic equations to make them easier to solve. There are three laws that we're going to see in total. The first law is the product law, and it looks like this. If I have log of mn with the base of b, I can split that up into log of m base b plus log of n base b, okay? Or vice versa. If I have log of m plus log of n, I can combine that into log of m times n, okay? Let's do a couple of examples here. Example number 1, I have log base 10 of 2 plus log base 10 of 5. I'm going to be able to merge those two together through multiplication because they have the same base. This will be log base 10 of 2 times 5, and 2 times 5 is 10. Now this question is actually solvable because what it's asking here is, well, 10 to the power of what is 10? 10 to the power of what is 10? And the answer is just 1. Right? 10 to the power of 1 is 10. So we could actually solve that one. Let's do another here. Log of x plus log of 4x. Again, through the law of multiplication, they have the same base, so I can bring it all together under one log. X times 4x, which is 4x squared. Nothing more I can do with this one because it's still working with the variable. And last but not least, oh, it got cut off here. Log a plus log b squared plus log of c cubed. Again, we can bring it all together because they all have the same base. This is going to be log of a times b squared times c cubed, all under one log. All right, that's our product law. Now, very similarly, we have the quotient law. And just how, like with exponent laws, the product and quotient laws are sort of inverses, that is also the case here with the quotient law with logs. Okay? If I have log of a fraction, I have an m over n. That's like saying log of m subtract log of n. Okay? And again, everything has to have the same base in order for us to do anything with it. Let's see what this looks like in practice. So I have log base 3 of 405 minus log base 3 of 5. So I'm going to combine these all together. Log base 3 of 405 divided by 5. And I can actually do that. 405 divided by 5 is 81. So now I ask myself, okay, can I actually solve this? 3 to the power of something, does that give me 81? The answer is yes, the answer is 4. 3 to the power of 4 gives me 81. And so that one was actually solvable. Log of 6 minus log of 3. So this will be log of 6 divided by 3, which is 2. This one is not solvable. I have a 10 here. 10 to the power of something is 2? No, that's not possible. So we're just going to leave it as log of 2. Last one here, log of 4x, take away log of x. This will be log of 4x divided by x, or just log of 4. And again, is 10 to the power of something 4? Is that possible? No. And again, I know it's 10. There's an invisible 10 down here. When there's no base written, it's always an invisible 10. Okay, so when this is the case, when you can't actually simplify it, this is your exact answer. So if you are being asked for an exact answer, this is the one that you should be giving, okay? At no point in time should you be giving a decimal by typing it into your calculator, unless specifically you are asked to approximate, okay? The last log law that we're going to be talking about here is the power law. This one's fun. The power law says this. If I have, again, same base or with one base, if I have a variable in my question that's being raised to an exponent, okay? So in this case, x to the power of n. I can actually bring that exponent out front and multiply it by log of the base of the variable. Okay, it allows you to sort of get rid of exponents and bring them down front. Okay, I'll show you what we mean in a couple of practices here. Simplify. So here I have 3 log 10 of 5. Okay, this one I'm going to be going in reverse, right? I have a 3 and I can bring it up front here. Log base 10 of 5 to the power of 3, which will be log base 10 of 125. Okay, vice versa. In this example, I have log base 5 of the square root of 125. Remember with square roots, that's like saying we have an exponent of 1 over 2. And so I can bring that 1 over 2 out front and then just have my question log base 5 of 125. Well, log base 5 of 125, 5 to the power of what is 125? That's actually just 3. And so I would have half times 3, or just 3 over 2. Makes it pretty easy to solve. Okay, last one here. Let's combine these. I have 2 log 5 plus half log 16. Okay, I'm going to bring the outside coefficients up as exponents. So this will be log of 5 squared plus log of 16 to the power of 1 over 2. Well, 5 squared is 25, so I'll have log of 25 plus log 16 to the power of a half is like saying what's the square root of 16, which is 4. And now I'm actually going to simplify using our first log law, which said that they have the same base, so I can bring them all into one term by multiplying. 25 times 4 is 100. And remember, this is a base 10. So 10 to the power of what is 100? 2. 2 is the answer there. Okay, we'll do 2 questions similar in that thought pattern where you actually are just having to sort of manipulate things. Here's our first one. Simplify 3 log x minus log x squared. In this one, I'm going to bring my 2 out front so that I can combine them. 3 log x minus 2 log x. This is sort of like combining like terms, right? I have, oh, I dropped an x here, but I have a log x and I have a log x with our coefficients, so I can combine them. 3 log x's minus 2 log x's is just log x. We can't actually solve this one because x is still a variable, so I leave it right here. And let's look at a super complicated one here. We're asked to expand this. So this is the simplified form. We are being asked to expand. Okay, there's lots of different laws that are going to be at play here. The first one I think I'm going to use is that division one so that I can separate this fraction out. So I'm going to have log of the cubed root of z to the power 4, take away log xy squared. In my first term here, the cubed root z to the power 4 I'm going to rewrite that exponent as 4 over 3. Right? The 3 is the type of root that it is that goes in the denominator. 4 is the current exponent, it goes on top. And then I'm actually going to use my multiplication law here, and I'm going to split this into 2 where they're being added. So this is going to be log of x plus log of y squared. And I'm putting these in square brackets here as a reminder that there's this subtraction sign that will need to be distributed out. With my first term here, it looks like I can bring my exponent out front now. That's nice and easy. So I'll have 4 over 3 log of z minus log of x minus log of y squared, and then for my very last step, I'm going to take my 2 on my y squared and bring it out front as well. So I'll have 4 over 3 log of z minus log of x minus 2 log y. This is now our fully expanded form. There's nothing further that I can do in terms of breaking terms up or in terms of bringing exponents out front. Okay, fully expanded, and that's everything you need to know about log laws. Just wait, one more thing actually. Here is this really interesting conundrum. When we plot a function f of x is equal to log of kx, it instead looks like we performed a vertical shift. Let me show you what I mean. So I'm going to open up Desmos here. And I'm going to just type in our log function. Y is equal to log x. Okay, this is what your untransformed parent function looks like. But notice how if I do y equals to log, and I'm going to do a horizontal, what should be some kind of horizontal compression. I'm going to do 100x. Doesn't look like anything changed, huh? The shape of the graph is very similar. It just looks like it shifted up despite the fact that I applied a transformation. I bet we can use log laws to explain this. So if I have my function is log of 100x. The 100 here, this should be a horizontal compression. With log laws, we know that we can split this up into 2 terms that are being added. I would have log of 100 plus log of x. Now hold your horses. Can I actually simplify my first term here? 10 to the power of what is 100? Well, that's 2. And if I move my 2 to the back, well, gosh, doesn't that look like a vertical shift? So sneaky, eh? So that's why any type of horizontal stretch or compression you do is just going to be looking like shifts because of log laws, which is pretty neat.